Okay, here is the sign. Let's see. I wanted to get to the axes. I wanted to show the axes on this. So Z is vertical, X is coming out of the page, Y is to the right. So you're going to have a force coming in and out of the page, the wind force, uh, maximum wind loading, 900 pascals across this area. The weight now, so this is Z, this is Y. The wind loading will cause a moment about the y-axis. It will also cause a moment about the z-axis. But since the wind loading is parallel to the x-axis, no moment about the x. The weight will cause a moment around the x-axis, which is coming out of the page. The weight coming down here. And it will cause, it won't cause, since it's parallel to the z, it won't cause a moment around the z-axis. And the line of action intersects the y-axis, so there won't be a moment around the y-axis either, due to the weight, just the weight, not the wind force. So we're going to have moments in all three axes, but they are due to two different sets of forces. Okay, so weight of this much, the area. So here we have the area. We can get the loading. You have to use vectors, and you can figure this out. Here's what I was talking about with the moments. Moment about point A, this point right here. Here you have the gravitational force, so it will not create a moment around the z-axis, but it will create, or the y. So here's that weight. And when you do the r vector, which is going to be 5.25 meters in the z, there it is, there's 5.25, 3 meters in the y, there. So this is due to the weight, this factor right here. This is due to the wind loading, and it's only along the x-axis. Let me see. Is that what we figured? Oh, here we go. Here's wind loading, 13.5 kilonewtons. And you crunch the numbers, you get this. So MA, yeah, crunch the numbers, you get MA equals all this stuff. That's MA. So now, and then we have a force down here also. And we're just balancing forces now. Oh, we've already done it. Okay. So I wanted to go through the strategy of approaching a three-dimensional problem. So we're going to do force and moment diagrams next. And so we want to know how forces vary along a beam. And the reason, there's a couple reasons. Here's a couple examples here, just to show you why this is important. That bicycles, for example, they want to be as thin and light as they can. So if you had a tube wall thickness that's constant, it's going to add more weight. But when you do this, you can put extra mass where the forces are the highest, and then reduce the mass where they're lowest. The overall goal being to reduce the weight of a bicycle. Here's another example. This is a skyhook. The idea of this is that you have a um, a ribbon that leads from geostationary orbit about 22,000 miles above the Earth. Let's see, around 40,000 kilometers. Is that it? And you lower a cable down to the Earth, and it's a space elevator. You can get objects from the Earth to this orbit, geostationary orbit, using an elevator rather than rockets. And it looks at constant stress, specific strengths, and that is how much strength does a cable have, and we're going to keep the stress constant as we go away from the Earth. What's kind of amazing is if you can get 100 megapascals, kilograms per meter cubed, which is reasonable. Carbon fibers are like 600, and that's the green line here. And the red is infinity. If you had an infinitely strong material, you could follow this red line. But the green line is still pretty darn good. That it's fascinating that we can think about launching vehicles into space by using an elevator. And we'd have to have a special cable that meets this kind of design criteria. Now, if the cables were not as strong, these are actually steel and aluminum are right about here too at 100. The carbon fibers are more like 600. This is kind of close to a plastic. So if you made it out of plastic, you'd have this big fat thing going on. So, but even metals get up into this range. So this can be very interesting. Glass fibers, fiberglass instead of carbon fibers, and so on. And we can make glass, fiber optics, we can make glass as long as we want. Okay. So we construct the diagrams much like we've done before. So here's a distributed load, here's a point load. We divide the beam up into sections, and we analyze it just like we did before, except now we're going to use X is going to be a variable. And we look at this section and this section and this section separately. But the analysis is identical to what we've done, what we started with the chapter. So resolve the forces, find the reaction forces and moments, find them parallel and perpendicular to the beam, draw your diagram. X distance is distance from the end of the beam. Y is either force or moment. So here's two diagrams, shear force and moment. Two diagrams, but they're placed on top of each other so we can see both at the same time. So this section right here is dividing up the beam into the three sections. That we have to consider this first, and the distributed load stops here. So this will have a new free body diagram, this section here, and this will have a third free body diagram because you're transitioning force all of a sudden. And this is a plot, the shear force versus distance along the beam, and the moment versus distance along the beam. And what we have is that the force is continually decreasing till it reaches a certain point. Then in this region it's constant. And then this point force is a step, causes a step. And it goes over like so. Okay. Moments. This is curvy. No forces in this region, distributed or point loads. straight line, discontinuity or discontinuity in the derivative. We're going to get into that in a minute when we do the math. Okay, so I'm going to stop the video here and pick up with the next video.